We are still working on all these objectives. One of the things we're going to talk about to start off with today with the graphing calculator, which again, you think, well, what are we using a graphing calculator for? Yesterday, we had to use it because we had options for what we could prove, and we didn't know which of those were actually provable. Today, we're going to use those to talk about situations where the proof can't happen, where you're looking for a counterexample. So we're going to be able to apply strategies for proving identities, and that'll include trying to find a counterexample and prove algebraic and trigonometric identities. And here's our little disprove, or finding a counterexample. And that's what it's generally referred to as in geometry and beyond. This book mentions disprove. And when we're proving the trigonometric identities, we had these wonderful boxes to kind of help us if we get stuck, things that we can go through and do. And if you weren't here yesterday, quick reminder that when you look at the worked out solutions, I made those so that if somebody is stuck and they're having trouble, that they should be able to use sine and cosine to make their way through the proof. So your proofs, if they're shorter than that, and they actually follow all the properties that we've talked about, that's fantastic. The homework at this point, the worked out solutions, are definitely for those that are struggling and trying to figure out how to get things to work. So I looked at this last night and thought we don't have a tremendous amount left today, which is kind of good. We have some work time. Disproving non-identities or finding a counterexample, that's really what we're going to be doing. Obviously, not every equation involving trigonometric expressions is an identity. They don't all work. And how can we spot a non-identity before embarking on a futile attempt at a proof and try the following exploration? Yeah, you don't want to do that, because what I mentioned yesterday was your proofs start out small, they get bigger, and then they should pull themselves back in. And if you find yourself in the situation where you're out here and it's just going and going and going, something's wrong. Either it's something you can't prove, or you made a mistake and you should just erase and start over and go a different way. So this one says we're going to prove or disprove that this is an identity, and that's that the cosine of 2x equals 2 cosine of x. Easiest way to see whether or not this isn't going to work is graphically, because like yesterday, if it works, they should graph exactly the same. So that would be what we would do. So let's grab our calculators and let's try it. Make sure your mode is in radians here. And we had cosine 2x on one side. Oops, and I'm not in the y equals. There we go. And then on the other side, basically saying, it doesn't matter where the 2 goes. Put the 2 wherever you want. It'll be the same. Well, we should already know that's not true. That's not going to happen, because we know that the 2 in front is the amplitude, and the amplitude is different for these. So now I go to my window. Maybe I'll just take a look at negative 2 pi to 2 pi again. And I did see a 2 in the front, and we do know that's amplitude, so negative 3 to 3 should be fine for our y's. And obviously, they are not the same, So this would not be something that we can prove. This is not going to be an identity. And what you do to show a counterexample is just find one spot where things are not the same. Well, we have plenty of spots on this one where things are not the same. So with the help of the graph, find a value for x for which the cosine of 2x does not equal 2 cosine of x. I'm always going to shoot for the easiest spot, and there it is at 0, right there. So if we put a 0 in, x equals 0 radians, we definitely see that the cosine of the quantity 2x does not equal 2 times the cosine of x. One counterexample was all we needed. There's plenty of them up there, but that's the easiest one. So we can see the y values completely different. And from what we know, like I said, about amplitude, we knew that was going to come. So now 3 says, does the existence of the x value in part 2 prove that the equation is not an identity? Yes, it does. We only need one counterexample to disprove what's going on. So yes, it is a counterexample. One situation where it doesn't work, and that's enough. Down here, it says graph y equals the cosine of 2x. And then this is interesting. Y equals cosine squared of x minus sine squared x in the same window. Now that one's not obvious. You know, I think in the first one it was like, we're going to see two different graphs here. This is not going to work. But with this one, we're not real sure about that. So definitely we would want to pop that in the graphing calculator and take a peek. Alrighty, so we have our cosine of 2x. And then we have to put cosine squared of x minus sine of squared x in there. And remember, the calculator doesn't do shorthand. So parentheses, cosine x, parentheses, parentheses, squared. It's hard to see the buttons when I get up that close. Where is my squared? Nope. This is why I like using my handheld. Right there. Whew. Looked like a cube that close up. So cosine squared of x, and then I need minus sine squared x. So minus parentheses sine of x, parentheses, parentheses, squared. Our window's not really big, but hopefully would give us a good enough look that we would be able to venture a guess as to whether or not these are going to work. So I hit graph. So our educated look at this graph would say, hey, they appear to be the same. I mean, that's what I'm seeing from negative 2 pi to 2 pi. So do the graphs prove, once we've seen it, that that's an identity? No. Visuals are never enough. You can't use visuals to prove things. Does it send us in the right direction? Absolutely. I mean, we'd want to know, can I prove this? Can I use what I know right now? Actually, this one would take a little bit more than what we've been doing so far. But no, it's not a proof. It's not a proof. Now, why isn't it? Why doesn't just a visual work? Well, I didn't graph this forever. I only graphed it from negative 2 pi to 2 pi. I don't know what's going to happen out there at negative 3 pi and 3 pi, negative 1 million pi and positive 1 million pi. Now, my logic tells me what I saw is probably enough, and they actually do equal each other, but it is not a proof. To prove something, you must prove it works for all values in its domain. Oh, hang on. English teacher would be mad at me. It's. Only when it is, and I used a hyphen, shouldn't be doing that. So that's why we're doing these proofs. If they're going to call it an identity, we have to make sure, yeah, it does always work, no matter what. And that means following the rules that we know, the properties that we know so far. And there's going to be a lot more of those coming, but for now, let's stick to the ones we have. And you look at this and, oh goodness. So identities we use in calculus, huh? So should I memorize all of those? I mean, that's a lot. Memorize, no, but these, we can get there. These, we know enough that we could prove. All of these. And it takes a second where you think, okay, how can I break this up? I mean, this is cosine cubed. I don't have anything with cosine cubed, but I have cosine squared. So if I could do cosine squared times cosine, maybe I could figure out a way to do some substitution and this would work. So cosine squared times cosine, oh, now that makes perfect sense. Because we'd subtract sine squared from one side and away we go. That'd be a nice little short proof. And as you look at some of the others and you see the 1/2s in here, these two, we don't have enough yet. The double angles. That's what we see here with the 2x, double angle identities. We don't know those yet. Down here, we could do those. That's about powers. We know stuff about powers right now. That's what we need to do today. So we have 2 of these. Example 6 is proving an identity that's useful in calculus. And we want to prove the following identity, that sine squared x times cosine to the 5th of x, wowzers, equals sine squared x minus 2 sine to the 4th of x plus sine to the 6th of x times the cosine of x. Oh my. Well, let's start with the easiest thing. We could separate one of those cosines out of there, right? And this one, by separation, could lead me to this one. So even though it doesn't look like the more complicated one, I'm going to start over there. So I'm going to pull one cosine out separately. And start putting some parentheses in because they had parentheses in theirs. So now I start thinking about the other set of parentheses and where I need to go. Oh, it has all sine in it. There's no cosines in there at all. So I think to sine squared x plus cosine squared x equals 1. It's got powers in it. So let's see, if I could break this up into cosine squareds, then I could substitute 1 minus sine squared in for it. So let me break that up. And don't forget your equals. Remember, those break up your steps. So I can't use the cosines. I want sines. So let's see. I'll leave my sine squared x here, but I'm going to replace each of my cosine squared x's with 1 minus sine squared x. I want you to take a look at that. We started really small, and we got bigger. So we need to figure out if this is heading us in the right direction or not. So take a look at these two that are in the middle, those two binomials. If we multiply those together, can you see how things might start to happen that we need? So let's do that. Let's multiply those two middle binomials together. Closer, right? So what's left? So that what I have down there in my last line will look exactly like the right-hand side up there. What do I have left to do? On? So what we just multiplied by, if we multiply that by sine squared x, you're seeing the future, and that's going to do it. All right, let's try it. By golly, look at that. So breaking it up into squareds, substituting 1 minus sine squared in for anything that said cosine squared, and we're able to get there. So again, not memorization, just being able to say, well, here's what I know. Here's what I can do from the trig, and doing some substitution. So now, b says sine to the fifth of x. Don't have you do this very often, and I'm a little worried about it because of one of my Algebra 2 classes. Half of the students are now out because they've been exposed to COVID. But I think if we're real careful, I want you to think about your plan for this one, what you would do, and talk to one or two other people just within the little 6 feet bubble here, 3 feet bubble that you have, and see if you both have the same plan for this one. I'm an eavesdropper, and some of you are talking this one through all the way and you're writing it down. I'm not going to stop you. Go ahead. Do it. And check in with those people that are next to you and see if they're doing the same thing that you are, and find it. All right, there's the bad thing about spring. There's a bug. And they love the light, so they're always on the smart bug. I thought about making a mistake so you would have to catch it, but I don't think there's any spots in here that it wouldn't be incredibly obvious that I'd goofed up. This is the plan I heard when I was wandering around. You know, people said, we'll break it up so that we've got one of these sine x's sitting here by itself, get the other one into sine squareds, and then substitute in with the Pythagorean identity. Was that hard? No. Yesterday we might have said this looks impossible. I don't know if we can do this. But today you've got a little bit of these problems and you've practiced them, and so now it's not so bad. That's as far as we need to go today. That's it. So we've covered those counter examples. I do want to let you know, because when you get to this page, I don't know if we put it in your notes packet or not. Some people get really scared. It is in your pack of stuff. It's a green worksheet because we're starting to see a lot of formulas. I don't know if you noticed that, but we're starting to see a lot of formulas. And when you get to this sheet, I want to remind everybody there are some of these we expect you just to know. And that's going to be everything down to here. The odd evens. And we do. We know those. We've been using them. That's not a big deal. What we see on the bottom of this page is what we were introduced to in a few of these today, which is what's up with the 2x thing? You know, what if they do cosine of 2x? How do you deal with those double angle identities? And we're going to get to those in a matter of a few days here. These, the sum and difference identities, double angle identities, power reducing identities, half angle identities, when we have you use those on a test, we're going to give you those formulas. You will be given those. These are not formulas that people that work with trig every day memorize unless they're using the exact same one. We look them up. That's what we do. So these formulas, hey, we could probably derive them eventually, but for now you just need to know they're there, and we'll give them to you on the tests. But there's 5-2 day 2. So without scaring anybody away, hopefully you can find that green sheet. We will, and one of the reasons I talked about it today is because we're going to need it in the future. We're going to start talking about the formulas for those. So you might want to dig that out of your huge pile of stuff I gave you. I see a lot of people have it already now. So that it'll be ready as we get into those sections. But look at that. Only 20-something minutes of notes here. Lots of work time. Love it.